My name is Tom Waters. I am a senior scientist in the museum's Center for Earth and Planetary Studies. And I want to thank you all for coming here this evening to the third lecture in this year's Exploring Space series. This program would not be possible without the generous contributions of our sponsors. And I'd like to thank and express my appreciation to Aerosjet for sponsoring this program. And we are forever grateful to NASA for their support, which they have generously given us for many, many years. In the audience tonight, I'd like to point out two people. One from Aerojet, that's Roger Myers. Roger, could you stand up? And representing NASA for us this evening is Jim Green. Jim, would you like to stand up and take a hand too? Again, we'd like to thank both Aerojet and NASA again for their generous support. Now, it's really a distinct pleasure for me to introduce tonight's speaker, Sean Solomon, who you've already met to some degree. Sean received his PhD in geophysics from MIT, where he was a professor of geophysics prior to becoming the director of the Department of Terrestrial Magnetism at the Carnegie Institution of Washington. Sean is a member of the National Academy of Sciences. And if I listed all his awards and accolades, there would not be time for the lecture this evening. In addition to his many accomplishments, he is the principal investigator of the Messenger mission. And tonight, he's going to tell us about Messenger and what we are learning about our closest planet to the sun. I have the real privilege of working with Sean on the Messenger mission. And I can tell you, it's really an experience of a lifetime. With that, I'd like to introduce your speaker, Dr. Sean Solomon.
Thank you, Tom. Let me get this started and take you on a journey to the planet Mercury, or as the daughter of one member of the audience might have said, one of those dumb planets we have to learn about. Okay. The word Mercury evokes many things. It evokes speed, it evokes changeability, it evokes temperature. It's the root of many of our words, and of course, it's one of the classical planets of our solar system. It's the smallest of the planets, the smallest of the classical planets. It's only 5% of an Earth mass, and despite that, it's made out of the densest materials. Maybe I shouldn't use this, of all the planets. And we know simply on the basis of the density that Mercury is mostly metal. It's 60% or more metal by mass. And it's got a rocky outer shell that's relatively thin. So Mercury is one of those inner planets that includes the Earth, Venus, Mars, and Mercury, that formed by common processes involving the aggregation of small bodies that collected into larger bodies. But the outcomes of those experiments all turned out very different. I'm going to move this a little bit away from me in the hope that there's less feedback. Anyway, Mercury is one of the oddest of this planet family that includes our Earth. And the journey we'll take tonight, that our spacecraft has taken, is illuminating many processes of planet formation and evolution that must have influenced our Earth and yet also produced Mercury as well as the Earth. We also now appreciate that there are many planets around other stars in our vicinity of the Milky Way galaxy. And what you're looking at is a plot of the positions of the known extrasolar planets as a function of the distance from their host star and the eccentricity or ellipticity of their orbit. And Mercury falls right in the middle of this cloud of planet orbits for planets around other stars, most of which are much, much larger than Mercury. because we can't detect objects as small as Mercury. But this tells us that Mercury is our closest laboratory for studying processes of planet formation and evolution near a host star, in this case our sun, that has great generality to a number of bodies that is now exceeding 1,000 or more as we learn about planets around other stars and how common planet formation has been. Before the mission Messenger, which I'll talk about in a few minutes, there had been only one spacecraft to visit Mercury, Mariner 10, which you see the trajectory here, was launched from the Earth in 1973 and flew by Venus once and then flew by Mercury 3 times, twice in 1974 and once in 1975. Mariner 10 imaged about half the planet because the same side of the planet was in sunlight at each flyby. It discovered that Mercury, like the Earth, has its own global magnetic field. Mars and Venus, by the way, do not. It detected some of the species in Mercury's very tenuous atmosphere, and it documented some aspects of what's called the magnetosphere, the volume of space around the planet dominated by the magnetic field, much like the magnetosphere that surrounds our Earth and protects us from a lot of energetic particles. And Earth-based astronomers filled in, prior to Messenger, everything else that was known about the innermost planet. It was radar astronomers in 1965 that discovered that Mercury was not, as had been thought then, in a synchronous rotation with the same side facing the sun as the moon faces the Earth, with its same side at all times, but was in a 3-2 spin-orbit resonance, so that 3 days, 3 sidereal days, to use the technical term on Mercury, are precisely equal to 2 periods of revolution of Mercury around the sun. That's the only object we know of in that odd resonance. And Earth-based astronomers filled in more of the species in the atmosphere, including sodium, then potassium, and then calcium. And these are odd elements for an atmosphere, and tell us that it is the planet itself that is the source of these species. Then 20 years ago, Earth-based astronomers discovered, and you see an image here, polar deposits that have the property that they reflect a great deal of radar waves that are sent to the surface in the same manner of reflectance and depolarization that is well matched by ices on outer solar system bodies and on the poles of Mars, leading to the idea 20 years ago, one of the ideas that Messenger is designed to test, that Mercury, the planet closest to the sun, also has ice near its poles in the floors of impact craters, and I'll come back to that story. And then finally, Earth-based astronomers discovered that Mercury must have a molten outer core in order to satisfy the motions that it exhibits in the course of its year, in its journey around the sun. So with Mariner 10 discoveries known, and with the Earth-based observations known, the Messenger mission was designed to answer the 6 questions that you see here. They're very basic questions about planets. And if we answered them from Mercury, we would be answering them more generally for all of the inner planets. That we would be expanding our ability to think sensibly about how our own Earth formed and how its geological history evolved and differed from that of its sister planets. Why the Earth, like Mercury, but not Mars, and Venus have a magnetic field, et cetera, as you go down that list. Furthermore, each of these questions could be answered from a Mercury orbiter and help us design the specific set of instruments that we would carry on our spacecraft. But before last March, there had never been a spacecraft in orbit around Mercury, and here are 2 of the reasons. It's energetically difficult to get a spacecraft in orbit. You have to slow it down by an enormous amount because a spacecraft sent from the Earth in toward the sun speeds up relative to a body like Mercury. And to go into orbit around Mercury, you have to slow down. And that's cast in terms of what's called delta V, change in spacecraft velocity. The second challenge is that Mercury is the closest planet to the sun, and the sun is extraordinarily hot, and the planet itself gets very hot, and so that's an environment that is hazardous to spacecraft. The Messenger spacecraft addresses these challenges. It addressed them in several ways. The thermal hazard of the sun was addressed by a sunshade, a ceramic cloth that is always between the spacecraft and the sun. There's a model, a 1/10 scale model up here that you can see at the end of the lecture to see what this sunshade is. And it uses a cloth that was commercially available, it wraps around the shuttle main engines and could be sewn onto a titanium frame. The spacecraft also had to address the challenge of the large cumulative change in velocity that was needed to go into orbit around Mercury. And it did that by building a propulsion system that was fully integrated with the spacecraft and that carried such large fuel tanks. Yes. The mic is a little too close to your mouth. I bet you all know this. If you can swing it out, it will clear up. Let's see if that works. Is that better? Okay, thank you. Thanks, George. Our propulsion system, by the way, is a product of Aerojet, the sponsor of this lecture series, and we are delighted to say it's worked wonderfully ever since we have launched. But this spacecraft at the time of launch was a couple of fuel tanks and a propulsion system and a few instruments as well. Our launch mass was 1,100 kilograms, of which 600 of the 1,100 was propellant and oxidizer. So we needed a huge amount of propellant and oxidizer. We needed to lightweight the spacecraft in order to accomplish this mission. And the reason is that it was a very complicated trajectory. In order to go into orbit around Mercury, we needed to take advantage of planetary flybys, 6 of them, to slow the spacecraft enough so that our propulsion system, as capable as it was, could do the final orbit insertion burn. And what you're seeing is the path that Messenger took over 6.5 years. We're looking down from the celestial North Pole on the ecliptic plane. And you're seeing all the orbits that the spacecraft had to make around the sun, 15. And you're seeing a timeline at the bottom of all those planetary flybys, 6. And the major propulsive events that our propulsion system had to satisfy, 5, before the orbit insertion burn last March became the 6th major propulsive event. And all of those stages had to be done to near perfection in order to be in a position to go into the orbit we wanted around Mercury last March. Here's our payload. You can look at those instruments. You'll hear about many of them. But let me simply say there's an imaging system, there are geochemical remote sensing instruments, there's a magnetometer, an altimeter, charged particle spectrometers, a surface reflectance spectrometer. And they're all chosen very carefully on the basis of the questions that we set out to answer when we designed the mission, and we hope to answer with observations from these instruments from orbit around Mercury. If you ever get a chance to go to a planetary launch, do so. It's terrific. Messenger was launched at night in summertime in 2004 on a Delta II Heavy. I didn't get to say it while they were still in view, but it had the 9 solid fuel boosters strapped on, 6 ignited on the ground and 3 in the air. And it was a wonderful experience to see our spacecraft, on which we've been working for several years, finally en route to Mercury. Of the 6 flybys of planets, 1 was of Earth, 2 of Venus, 3 of Mercury. Here you see, looking down from Mercury's North Pole, the trajectories that we followed on the 3 flybys. So the first flyby was in January 2008, then October 2008, and then almost a year later, September 2009, the 3rd flyby. And then we had an 18-month wait until Messenger, now going around the sun only slightly faster than Mercury itself, caught up with Mercury for the 4th encounter and our orbit insertion. And here was the glorious application of our propulsion system. Thank you, Roger. When we did the orbit insertion burn on St. Patrick's Day night, local time, 15-minute burn, perfectly executed. And we ended up almost precisely in the orbit that we had designed, and we're ready to start orbital operations. This is the orbit we're in now. It's actually today's orbit as viewed from the Earth. It's a highly elliptical orbit. That's for reasons of thermal design, which I can explain if anybody's interested. It's about a 12-hour period, a little longer, and nearly polar, inclined 82.5 degrees to the equatorial plane. And you see some of the statistics. of how far we are from Earth at any given time, namely today, and how far Mercury is from the Sun, and all of those quantities, of course, are changing every second. Okay, let me go through some of the topics that we have addressed through the observations to date, but say at the outset that we intended to go into orbit and take observations for 1 Earth year. We're not even 2 months into that orbital mission phase. The questions we set out to answer require, in many cases, a year's worth of observation, so we're not yet in a position to answer all of them. But we've learned a great deal about Mercury from the flybys and from the first 6 or 7 weeks of observations. And so I want to give you an overview of some of the aspects of one of our sister planets, the smallest, and what it's telling us about planets of the Earth class. As I mentioned, Mercury has a magnetic field. We knew that from Mariner 10. The flybys added to what we knew from the Mariner 10 flybys. And now we're taking magnetic field data every orbit, and we've accumulated nearly 100 times as much information as we had from the flybys. But we're doing so globally, which we can now do for the first time. And we can represent the magnetic field, as you see here. The details are not important. What is important is that the field is very Earth-like. It is nearly that of a magnetic dipole, or equivalently a bar magnet, very near the center of the planet, a little bit offset. That's turning out to be interesting. The magnetic north pole of Mercury points to the south geographic pole, just as our magnetic field does, except Mercury's magnetic field is even more closely aligned with the spin axis than Earth's magnetic field. All of these are signatures of an origin for Mercury's magnetic field that is thought to be also very Earth-like. One of the mysteries is that Mercury's magnetic field is much smaller than that of the Earth, and we're still trying to understand that. But it looks like once we acquire a firm understanding of how Mercury's magnetic field continues to be generated, and we think has been generated over the history of the solar system, it will very much inform our understanding of our own magnetic field, how it has evolved over time, and what we can look forward to in the future. I mentioned earlier the magnetosphere, which is the envelope of space dominated by the planetary field. Because Mercury's field is so weak compared to the Earth, and Mercury is so much closer to the Sun, which carries its own interplanetary magnetic field away from the star with the plasma that we call the solar wind, constantly blowing outward from the Sun and governed by the equations of electromagnetism and plasma characteristics. Mercury's magnetosphere is much smaller as a consequence of being so close to the Sun and having a weaker planetary magnetic field. The dimensions are smaller than that of the Earth. The variations imparted by activity on the Sun are exaggerated, are amplified relative to what happens at the Earth. Everything happens much faster on Mercury, but we see a variety of phenomena in Mercury's magnetosphere that have some great familiarity in the magnetosphere that surrounds our own planet. It's just that everything is much larger in relative scale and is much faster. And you see that even our 3 flybys, as depicted in this cartoon on this slide, encountered Mercury's magnetosphere in different sets of state. And small differences in the magnetic field that was flowing with the solar wind plasma had a big influence on how the magnetosphere of Mercury was manifesting itself as we flew through. Ranging from the very quiet conditions that we saw in our first flyby to ones with a lot of activity in the second flyby to a really wild set of conditions under the third flyby. All during a period of fairly quiet sun. And well, now we're at Mercury. We're flying through the magnetosphere twice a day. The Sun is picking up in its activity, and we're seeing just a range of new phenomena that are bound to tell us a lot about how Earth-like magnetospheres operate. I said that Mercury has an atmosphere. It's very tenuous. It's very low in density. The technical term in planetary science for Mercury's atmosphere is exosphere, meaning that the density is so low that the atoms and the molecules of the atmosphere don't collide with each other. They don't behave like a gas, like what we breathe around us. The atmosphere is not something you can see or smell. It is so low in density. And most of the atoms in the atmosphere are things you don't think of in terms of our own atmosphere, like we talked about potassium and sodium and calcium. And they're derived from the rocks and the soil at the surface of Mercury. And here you see some of the mechanisms on the left of how atoms are knocked off the surface of Mercury by sunlight or by solar wind or magnetospheric ions, or the impact of high velocity dust, micrometeoroids hitting the surface. And some of those atoms are lofted only a little bit off the surface, they fall back down. Some are lofted high off the surface, and there they're influenced by sunlight. Sunlight can actually exert a sufficient pressure on individual atoms to push them away from the sun, and they stream away from Mercury, they're lost from the gravitational field, and they form a comet-like tail of neutral atoms that streams hundreds, in fact, more than 1,000 planetary radii, as seen by both Earth-based astronomy and our spacecraft. So during our flybys, we actually flew through Mercury's comet-like tail. And we had a spectrometer that could look for individual species. And here you see the way the spectrometer, which is fixed to the spacecraft, works. The spacecraft actually nodded about the sun-planet line as we flew in toward the planet. And each of these squares is an individual observation that we made at the specific wavelength where sodium atoms scatter sunlight by a process known as resonant scattering. And as we got closer to the planet, the total number of sodium atoms was larger and the total intensity was larger, and we could contour these data to produce maps of the sort you see here. And that tells us about where the sodium was being generated on the planet and where those atoms had enough energy to get high enough into the environment of Mercury to be pushed anti-sunward by light, by radiation pressure to form this tail. And in the case of sodium, it was at fairly high latitudes. You see both north and south. And we did the same for calcium, as you see in the middle, and as magnesium, as you see on the right. And to our surprise, we discovered that the distributions of those species in the tail as a function of latitude were different from one another, which meant that the combination of composition or source processes on the surface was different for the different species. And the tail was composed of many elements, but it was a mix of processes that we hope to unravel from orbital observations to explain how this very dynamic exosphere works. If we turned off all the processes that generated Mercury's exosphere, the exosphere would be completely gone in a matter of a few days. And so that says that there must be continuous sources of this material, and we're trying to learn which are the most important for each species and how all of these processes interact. And one of the expected but still dramatic results of our multiple flybys was that the strength of these processes do vary. And you see two snapshots of the tail of Mercury in sodium emission, and you see at the same scale of plotting that the second flyby produces a signal about 20 times stronger than we saw in the third flyby. And that's simply because Mercury was in a different position in its orbit, moving relative to the sun by a different amount, and these are factors that influence what we can see. In addition to the neutral species, Mercury is surrounded by ionized species. Some of those ions are ionized by sunlight, particularly in the ultraviolet. Some are trapped ions from the solar wind. And what you see here in this animation is the first fly-through of the ionosphere with one of the instruments on Messenger that measures on the spacecraft the density of ions that we're flying through. The plot on the top is the solar wind protons, and the plot on the bottom is heavy ions dominated by sodium as a function of position as we fly through. And you see that the heavy ions peak at closest approach, but there are other peaks. And throughout the magnetosphere, you can see both plasma from the solar wind and heavy ions. So now that we're in orbit, we're seeing the richness of the plasma distribution and the ion distribution inside Mercury's orbit. And again, it's a reflection of a mix of solar wind interaction processes and planetary processes that we hope to unravel. But it is also a very interesting probe of some of the material making up Mercury's surface. Let me turn to imaging, which has occupied a lot of the results that we have dealt with on the Messenger mission. And what you see here is a depiction of the coverage that we obtained with our imaging systems on the 3 flybys in comparison with what the area that Mariner 10 imaged, which is outlined in green. And between Mariner 10's 45% and the 3 flybys of Messenger, we filled in most of the planet with at least some kind of imaging. In fact, the coverage, since that's a projection that tends to overemphasize the areas near the poles, the coverage after the Messenger 3rd flyby was 98% of the surface had been imaged. But when I say imaged, that means imaged at some resolution and with some lighting conditions. Here's a wonderful comparison of a region on Mercury with an image on the left taken by Mariner 10 and one from one of our flybys on the right of Messenger. It's the same area, roughly the same resolution to the image, so nothing wrong with either Mariner 10 or Messenger in terms of the camera system. But what is different is that the illumination is completely different between the two, in that the sun is nearly overhead for the Mariner 10 image and is very low near the horizon for the Messenger image. And I draw your attention to that double ring impact structure in the center of that Messenger image, and I challenge you to see it on the Mariner 10 image. It's there, but under those lighting conditions, it doesn't show up. You need the shadows, you need the low sun to see many kinds of geological features. And what that says is that in order to have a global view of the geology of Mercury, we need not only to have global images, but we have to be able to control the resolution and the lighting conditions in a more or less uniform way around the planet. Let me say a few words about color. This is Mercury in what you might think of as true color. If you were able to ride on our spacecraft as it flew by and look with your eyes at Mercury, it would look pretty gray. There are variations in color, but they're hard to see. You can see areas that are a little bit red or a little bit bluer. But because these are digital images, our camera systems is CCDs, like in your camera, you can digitally enhance the variations in color, and you can accentuate those variations and begin to map variations in color as a proxy for variations in composition and discuss things like the range of aerial coverage of certain types of units that are characterized on the basis of their brightness and on their overall color. And here's one such representation of 2 of the hemispheres of Mercury in exaggerated color. These are not the colors that you would see, but you would see blue and you would see red, very subtle, that here is accentuated, so it's much more obvious. And there are color variations on Mercury, and there are large expanses of more or less uniform color, and so you begin to map geological units, as they're termed, that have common color and reflectance and are thought perhaps to have a similar composition and a similar origin, and you begin to build up an understanding of what you're seeing in these color images. Well, let me come back to that. But to show you some of what's coming out of our color mosaicing from orbit, where we have much better resolution, both in color and in monochrome. And we're building up a global color map under ideal lighting conditions. And again, it's exaggerated color. You're seeing an area near the North Pole of Mercury. But you can also see in exquisite detail some of the landforms and some of the variations in color that are almost certainly reflected of variations in composition of some of the units that you're seeing here. Messenger also is carrying out a global campaign of targeted high resolution. The color images that you saw on the previous slide might have an average resolution around 1 kilometer. We're taking a global monochrome set of images that will make a global mosaic with a resolution, an ability to discern features on the surface that's at least a factor of 4 better. But we can also use our narrow angle camera to take very, very high resolution images like these that have a resolution of 15 meters per pixel or 10 meters per pixel. We don't have the onboard storage or the downlink rate to take images at this resolution of the entire planet, but we can fill in the global mosaics with a targeted high resolution to try and get the details that are necessary to understand the geological origin of the features that we see on the global images. So here, for instance, you see a field of impact craters that are largely what are known as secondary craters. When a major crater is formed, it's an explosive event, leaves the surface and falls back down on the planet with a much lower velocity than the velocity that created the first impact. it creates secondary craters, which generally have a softer morphology, a softer shape to them, and often occur in these chains, or even these V-shaped features that you see at this high resolution. I want to talk next about volcanism. Volcanism is a major planetary process involving melting of rock at depth, and in many cases, the eruption of molten rock on the surface to change the surface of the planet, at least in a local area. Volcanism has created the floor of the Earth's oceans. We see volcanoes around the Ring of Fire in the Pacific. It's a very familiar landform that we understand in terms of natural hazards, in terms of the origin of many of the rocks of the Earth's crust, and in the rocks on the crust of Venus and Mars and the Moon. After Mariner 10, we didn't have enough information from the images that mission acquired to understand how important, or whether it was important, to study volcanism on the planet Mercury. But Messenger changed all that. And part of the story of the volcanic history of Mercury is contained in this large impact basin that's 1,500 kilometers across, was seen by Mariner 10. It's called the Caloris Basin. And in color, you see on the right here, that the interior of the basin consists of these very bright reddish plains. The exterior, out to several basin radii, consists of these darker, bluer plains. And we suspect that different colors correspond to different compositions. But an interesting question is what the age of these features are. We don't have any samples in our rock collections. We don't have any meteorites that we know come from Mercury. So the way that geologists studying planets date surfaces is to look at the craters that form after those surfaces were laid down. The denser the craters on a surface, particularly a volcanic surface, the older it is. The more lightly cratered the surface is, the younger it is. So this is a graph on the left of the density of craters. It's a log plot that compares the density on these two planes with the density of craters on features that formed at the same time as this impact basin. And what they show is that the planes are younger. They have fewer craters per area than the features that formed at the same time as the basin. So that's a vote that if for them to be younger, that they came later, they were in place later. They probably weren't in place by impact processes, but by volcanic processes. And we even have some examples around Caloris of what seem to be volcanoes. Their attention was drawn very early on the Messenger team to these reddish spots around the periphery of the Caloris Basin. And this one over here in particular drew a great deal of attention because it looks like this. You see it where it's located on the basin rim in the outer image, but the inset shows the detail that we got on the first flyby. And it's got an irregular depression. It's got bright deposits that seem to drape over older pre-existing terrain. There's an apron of these bright deposits with a very diffuse, irregular outline. And this looks, this is best matched in terms of planetary analogy with volcanic features on the Moon. And here you see some oblique views of some lunar volcanic domes that have dimensions that have the same characteristics in terms of interior depression and draping of distinctively differently colored deposits on top of pre-existing terrain. So this and other features like it are held to be examples of volcanic centers, much like these domes on the Moon, and are specific sites of volcanism that must be more numerous on Mercury than those that we can see so far, than those that formed the Great Plains, which we think now also are volcanic. But we don't have examples of the source regions of all volcanic materials on the planet. But there are now a growing list of features that have these irregular depressions surrounded by distinctive color deposits that we think are also candidates for volcanic centers over the history of the planet. And so we've gone from a situation where the importance of volcanism was unknown to one where volcanism seems to be quite widespread, at least as widespread as on the Moon. Here I want to show you one high-resolution image that showed up at our science team meeting just today of a little dome on the floor of an impact crater. The dome has a summit depression and a little cleft in the side, and looks very much like a volcanic feature known as the Cinder Cone. Here it is sitting on the floor of an impact crater. It's just a kilometer or two across. But we expect, as we build up these high-resolution images of Mercury, to see many, many more examples. Volcanism over the history of the planet was ubiquitous, and so we can add Mercury to the list of planets on which the surface and the crust was built up in an important way by volcanic processes of the sort with which we are very familiar on the Earth. The third flyby of Mercury drew our attention to this basin named for Rachmaninoff, the composer, and in particular to this structure, which is almost 300 kilometers across, and to the differences between these smooth plains inside this inner ring and those outside, between this ring and the rim of the basin. Because what we saw is that the inner plains were different in color. They had fewer craters per area, and they appeared to breach and flow out over, at one time, this inner ring onto the surrounding plains. And there were examples on the surrounding plains of some of these distinctive color units that surround irregular depressions. And all of these are signatures of volcanic processes. And so the only way that these plains can differ in composition from their surroundings and be younger than and have flowed over the boundary between the plains exterior to them is if they were in place volcanically well after this basin formed. This basin is so well preserved and has so few craters on it. It's one of the youngest impact features of its size on the planet Mercury. And so we're looking at the best example on the innermost planet of comparatively young volcanic activity. It still might be 1 billion years old, but it greatly extends the history of volcanic activity over what we knew before the MESSENGER mission. Let me say just a few words about faults and the great structures that they have created on the surface of Mercury. Tom Waters, who introduced me, is one of the leading experts in the world on these fault structures. On Mercury, many of the great faults are of the sort that accommodate shortening of the crust. They're called thrust scarps, thrust faults that produce at the surface cliffs, huge cliffs, 1 kilometer, 2 kilometers in relief, that have a nonlinear form on a map and are called lobate as a result, or lobate scarps. These things are nearly ubiquitous on the surface of Mercury and led to the hypothesis, now going back to Mariner 10, that they record a time when Mercury contracted everywhere, where the surface shrank in area. And the only way we know how to do that is if the whole planet shrank as it was cooling. As it cooled off from a hot initial state, as the temperature in the interior dropped, as this great body of metal in its core cooled off and partly solidified, that would have led to global shrinkage of the sort we see accommodated by these great scarps. And Messenger discovered that the region that Mariner 10 had not seen, indeed, had many more of these scarps, and even some areas that Mariner 10 had seen but at poor lighting, were shown to have scarps that Mariner 10 missed. But not all of the deformation on Mercury is that simple. This is another area that Tom Waters has studied in great detail and published several papers on. It's an area of very complex deformation. It happens to be in the center of the Caloris Basin, where not only has contraction happened at some point in its past, producing ridges and scarps, but there has been extension, stretching of the crust, producing these troughs that you see, some of which cut older ridges and contractional features. So it's a complex history that is telling us about the evolution of Mercury, and in particular the sequence of volcanic events and global cooling and subsidence and uplift events that are very reminiscent of tectonic processes on the Earth, but are here very well preserved from billions of years ago and can illuminate the early history of Earth-like planets. The very center of the Caloris Basin has an amazing collection of troughs, known as Pantheon fossae that radiate out from the center of the basin. Here are some very recent high-resolution images that we've taken from orbit of some of these features. Here, there you see a number of impact craters. Some of them are secondary craters. Some, like this great central peak crater, Apollodorus in the center, is a primary crater, and its connection with the troughs that almost seem to radiate out from it is still debated on the science team. But I leave you with the idea that Mercury has experienced a great number of Earth-like deformational processes by completely different mechanisms. There's no evidence for what on Earth we call plate tectonics, but Mercury nonetheless has experienced some of the most intense deformation of the inner planets, and that can only help us to understand these processes more generally on all the planets. This is a mosaic of some of the highest resolution color images we obtained from the flybys. We're doing better now, but I show you this image, or mosaic of 5 images, because it was made into an animation that I'll put on next, of a simulated flyby over Mercury's surface with exaggerated colors. And what it shows is the relationship of color as a marker for composition and structure and form of the geological features. And it's very instructive because it's also pointing to variations in composition not only laterally on the surface that we can map, but also vertically. And the reason is that impact craters, when they form explosively by the impact of a high velocity object hitting the surface, they excavate material from great depth, and they throw some of that material out beyond the crater rim, and they produce crater rims and central peaks to craters as a result of uplift following that great explosion. And if those materials differ in composition from the materials surrounding, it's telling you that there's material at depth below the target area where that impact occurred. Somebody's talking to my ear. Anyway, it's a poor man's probe of variations in composition with depth on Mercury. So let me play this animation. So again, this is exaggerated color. This is not what you would see with your eyes. But imagine that you were overflying the surface of Mercury and you could accentuate the colors that you see. You see great scarps that are deforming craters, such as this one here. But you see the color changing. You see that impacts have excavated bluer material than the surrounding brown. You see a crater called Calvino that has excavated orange material, red material for its rims, blue material for its central peak. You see a larger crater here that has thrown out blue material, but not everywhere, just to one side, as if the target area itself were heterogeneous. You see a bluish tan unit, but craters come along and punch through that unit, bringing up red material, indicating that red material is at fairly shallow depth. Another crater that has thrown up bluish dark material only to certain azimuths. Another crater that has exposed very different material. Mercury is turning out to be extraordinarily heterogeneous. We haven't yet mapped all of these colors into differences in composition. We're very close to doing that. But it has led to this kind of scenario for how we think the planet evolved. That is depicted in this cartoon on the right, that much of the outer surface of Mercury seems to have color characteristics that we can find and associate elsewhere with volcanic plains. But in a given region, sometimes you see only a single color until an impact comes along and excavates material of a different color from its surroundings that must be at depth. It looks like plains some other place farther away, and therefore most likely consists of plains that have been buried by subsequent volcanic activity, leading to the notion that there are a sequence of unevenly distributed volcanic deposits that make up kilometers of the outer part of Mercury's crust that we can begin to sample only because impacts have come along, dug deep enough through the impact process to expose craters, to expose materials by the cratering process as deep as several kilometers from the current surface. So our entire picture of the importance of volcanic activity, the formation of the crust of Mercury, and the evolutionary history of our sister planet has changed by the observations we made from the flybys, from one in which the importance of volcanism was unknown and debated, to one in which volcanism seems to have dominated, that plus impact cratering, almost everything we see on the surface in terms of the emplacement of the rock units we see. I want to end with an interesting story. We're on the almost end on the trail of answering, but we still have a long ways to go. And it goes back to the discovery 20 years ago from Earth-based radar that in the floors of impact craters, very near the north and south pole of Mercury, are radar-bright deposits that look, in terms of their radar characteristics, like ice, like water ice. Water ice elsewhere in the solar system, on the satellite of Jupiter or on one of the poles of Mars, where we've also looked with radar at what the characteristics are. And that's pretty astonishing because the temperature at Mercury varies between day and night by 600 degrees centigrade, 1100 degrees Fahrenheit. Huge range in temperature at the planetary equator between day and night. But the reason that hypothesis that there might be water ice in the floors of polar craters was not laughed off the street is that Mercury's spin axis, unlike the spin axis of our own planet, is almost perpendicular to its orbital plane, which means that an impact crater, a hole in the ground surrounded by a ring of mountains, if it's at the pole, never sees the sun. It's in permanent shadow. The atmosphere is so low in density that there's no transport of heat from the equator to the poles as there is in our atmosphere. And so looking out into black space, never seeing the sun, it's extraordinarily cold and remains cold, cold enough to store water ice. So we're carrying an instrument, a neutron spectrometer, that eventually, I don't have that answer today, will tell us whether that material is water ice. But as an intermediate step, we're looking with our imaging system and our altimetry system at these polar craters to explore this notion that they are indeed in permanent shadow. That's a requirement of the idea that they contain water ice, and that's the explanation for the polar deposits. So here you see the first profiles of altimetry that we obtained with our laser altimeter from orbit. Here you see some of the coverage in the northern hemisphere of Mercury with the color coding of topography as we begin to fill in the whole topographic map of the northern half of the planet as our orbit moves with respect to the planet every day. And you see that there's quite a bit of relief. That's 6.5 kilometers depicted in that color scale, all of which represented there on the surface of Mercury, some particular low areas, blue areas near the poles. But I want to draw your attention, if I go the right direction, to these areas. This is now a close-up of one of these radar images, this one from about 10 years ago, at somewhat higher resolution than the Discovery photos. This is of the North Pole. And all the bright areas on this image, draw your attention to 80 degrees north, 70 degrees north, so there's the North Pole. All these bright areas are candidates for polar ice. They're radar bright. This is a radar image. And one of those areas with radar bright materials was imaged in this polar mosaic obtained recently from Messenger. We've also flown over this crater enough times to make this simple topographic contour map, but we can begin to chart out the depth of this crater and to address the question of whether the floor of this crater, which has polar deposits, is indeed in permanent shadow. And the answer is yes, this particular crater is deep enough to be in permanent shadow in the areas where radar has imaged features that may be ice. But we're also imaging. What you see here in this animation are images of the South Pole taken at different times. And as we sweep out a solar day on Mercury, we will learn which features are in shadow only for a portion of the year and which are in permanent shadow, how those features correspond to those on the radar map. And ultimately, we'll be training our geochemical remote sensing instruments for enough time to sort out what the variation in composition is in this part of the planet and whether water ice is candidate material. We do have some early results from composition that I will end on. They don't pertain to water ice, but we're beginning to get information on what the surface rocks of Mercury are made of, and that is critical information for addressing the question of how the planet formed. The instrument that I will first describe is called an Xray spectrometer. The The sun is the source of X-rays that are particularly energetic when there's a solar flare. Those X-rays impact the surface of Mercury, and some atoms absorb X-ray energy, lose an electron, which then radiates another X-ray at a diagnostic energy by a process called X-ray fluorescence. And we can measure those fluorescent X-rays and say something about composition. And we've had enough flares since we've been in orbit to do those kinds of measurements now several times and make some preliminary statements about the composition of surface rocks. What you see on this diagram are simply two ratios of elements. What happened to my... There we go. Don't touch the wrong button. Of elements that are major rock-forming elements, namely magnesium ratio to silicon and aluminum ratio to silicon. And you see on this map where lunar highlands rocks show up, where most terrestrial volcanic rocks show up, where the asteroid Vesta, where a spacecraft is arriving any week now, looks like, on the basis of meteorites we think come from Vesta, as well as Martian meteorites, Mars rocks, and other exotic terrestrial rocks. Here's the average for the Earth's crust. Well, we can now add Mercury to this list, at least in a few areas that we have sampled from orbit during solar flares and can begin to map out these variations. And what happened to my plot? Come on, guys. Bear with me. This just adds to the drama. There. It was worth waiting for. Anyway, here are the plots for Mercury. And you see that they don't look like the moon, and they don't even look like typical terrestrial basalts. They're out here at very high magnesium values, like some very unusual rocks on the Earth. We've only begun to do this exploration of composition of Mercury, but this is not what any of the models of Mercury to date have predicted, so it's wonderful. We can throw out all of the ideas that have been in the literature for decades. Mercury is going to be a different place, and a place that is going to change the textbooks on how the inner planets formed as a function of distance from the sun. We also have a measurement from another instrument called a gamma ray spectrometer. Again, early measurements that are averages for the whole planet of radioactive elements that emit gamma rays in the course of their radioactive decay. The two of them depicted here are potassium, which is quite abundant, and thorium, less abundant. There's one isotope of potassium that is radioactive. And prior to the MESSENGER observations, there was a hint that the ratio of potassium, a fairly volatile element, easily driven off a planet by high temperatures, as ratio to thorium, which has just the opposite behavior, and what the geochemists call refractory, a kind of element that sticks around even under high temperature conditions, that this ratio decreased as you got to objects formed closer to the sun. The sun, the source of heat, even early in the evolution of the planets, was surrounded by a disk of gas and dust that increased in temperature as you went in toward the young star. But Mercury is coming up with a ratio that belies the trend and is telling us that it ain't so simple. And again, we're going to have to change our ideas for how planets formed, and how planets formed as close to their host star as Mercury did. So it's just a snapshot that I was able to give you in the short time today of what will be the first global look at one of our sister planets, admittedly the smallest planet, but one of the most interesting planets because it's so close to the sun, because it's made out of such dense material, because it records processes that happen close to a star that seem to be different from what we expected in terms of a lot of those processes. We've collected more than 18,000 images to date, as well as 110 orbits of all kinds of other data, and we're not even 1/6 of our way through our one-year primary mission. So we will, in the course of the next 10.5 months, build up the first global view of one of our nearest, but heretofore least understood planetary neighbors. And we hope that at the end, we will understand Mercury much better, and as a result of this detailed investigation of one of our siblings, understand our own planet and its place in our solar system much better as well. Thank you.
We have time for some questions, and so I'll just take questions and repeat, and we'll start with this young lady right here.
Thank you. I was fascinated by that diagram that they had, that Sean had at the very beginning, that showed the differing views, which showed that they really don't know what's inside Mercury at all. It showed,
Right.
the yellow and the
Right.
gunmetal gray and everything. At the end of this mission, will you know more of what's inside Mercury?
We will.
Okay, let me repeat the
Repeat the
question for the. Will by the end of the mission we know more about the interior composition of Mercury and structure?
What we know now is that the average density of Mercury for its size is very large compared to the other planets. And so that has led to the hypothesis that, like Earth, Mars, and Venus, Mercury has a central core of iron and other metals to satisfy that mean density. We know a lot about the Earth's interior structure, but for Mercury, that core must be much larger as a fraction of the planet than it is for the Earth to account for the bulk density. We will make measurements from orbit of the gravitational field and of the topography that together will give us new the measurements of new quantities that will constrain the size of that core. So we will have much more information than just the bulk density that will allow us to say the core is within a very narrow range of radii, and that will sharpen our understanding of how much of the planet is metal and how much is rocky. The chemical measurements we are making of the surface include chemical measurements of volcanic materials that were formed by partial melting deep inside the planet. And so we can work backwards from the compositions of the volcanic plains to the compositions of their source regions at depth. We can also use topographic and gravity information to constrain how much of the outer part of Mercury is relatively low-density crust, like the crusts that we reside on the Earth, compared to the denser silicate mantle that underlies it. So the answer is a lot. We will have a great deal more information, and the kinds of very simple cartoons that captured your attention on that first slide will be considerably narrowed in their range.
Okay, next question, center here. Yes.
It appears that the surface is being constantly bombarded.
Yes.
You're making measurements of the chemistry of the surface. Is there a big change due to that so that you're not really measuring the bulk chemistry?
So our impacts basically impact features.
Not impact features, just the sun, the bombardment that lifts the sodium off.
I see.
So are we looking at just the bare surface that's been changed by some constant characteristic, or are we really looking at the bulk chemistry?
Okay, are we looking at really the materials that are being reflected and measured? Are those just superficial, or are we looking at something that is deeper within the crust?
Let me answer your question in two steps, because the larger impacts do turn over the surface. They garden it, and they impart a contribution to surface materials from the material that's falling on the surface. So there is a component of the material on Mercury's surface that has come from this bombardment. And we see this on the moon. That we can find certain metals, certain signatures of asteroids and comets that over the history of the moon have imparted some of the material to the lunar surface. Nonetheless, the moon has taught us that this process does not dominate what we see. That we can see chemical variations from orbit. We can, astronauts have walked along the surface and sampled the rocks. And yes, there's gardening, and yes, there's some horizontal transport of material, but we can still map chemical variations that correspond to the rocks that we can see. So the mixing of meteoritic and cometary material is measurable, but it is not dominant. But the second process, and the one that might have prompted your question in the first place, is something known as space weathering. The combination of bombardment by tiny dust particles and ions does change the character of the surface. We see that in the darkening process that happens both on the moon and on Mercury. The youngest impact craters on both bodies tend to be bright, tend to be a somewhat different color from the rest of the planet. And yet those same kinds of craters, if allowed to be exposed to the space weathering process for enough time, and enough time on the moon is about 1 billion years, will darken to look like the rest of the terrain. So on the scale of micrometers or maybe even nanometers, there is a chemical alteration that is changing the color and the albedo of the surface materials. It's not changing the bulk chemical composition. It's changing the character of some of the constituents, notably iron on the moon, from silicate constituents to metal constituents. And we don't know what the darkening process is as well on Mercury. So that is indeed going on. But in spite of the knowledge that there must be this space weathering, we can see variations in color, and we're beginning to map with the elemental remote sensing variations in composition that are preserved even in the face of this space weathering. So again, we think we can unwrap the effects of space weathering and look to the actual Mercury materials and begin to sort out what the variations in composition are and what they mean for how the planet evolved.
Okay, next question, down front.
Yes, to our knowledge, Mercury has no moon today. Is it possible that it had one in the past? It's possible it was a very small one. You might describe.
Is it possible that Mercury in the past had a moon or a very small moon that Messenger perhaps may discover?
It is possible that Mercury had a moon or even has a small moon, and it is sufficiently possible that we have included in our imaging campaign some images that will seek out whether that is the case, at least put limits on the maximum size of a moon if we see nothing, and will announce the discovery of a moon if we see something. There have also been Earth-based searches for moons of Venus and Mercury that so far have been negative. There have also been postulated objects that reside in stable orbits inside the orbit of Mercury. And we've had quite an active campaign looking to see whether we see any of those with our imaging system. And again, those have been objects of studies from Earth that so far have been negative. And we have pushed, at least in the volume of space that we have searched, the upper limit down to a lower diameter than the Earth-based studies. Those things are called volcanoids after what was once thought to be an innermost object called Vulcan. But they're a wonderful theoretical construct right now, but so far we have no known examples. We will continue to look.
Okay, back in the back. Yes, I'm so, yeah. Yeah, yes, please, there you go.
So, the search for exosolar planets that potentially could support life focuses on those exosolar planets within a certain stellar habitable zone. Mercury, of course, fit that criteria. However,
Right.
you mentioned the polar craters, at the bottom of which could exist frozen water.
Yes.
Has there been thought that on perhaps the shoulders of such craters might be a intermediate temperature at which liquid water might exist and possibly be able to support life?
Okay, do craters on Mercury that we suspect may have water ice located in them have a zone in which the water ice might be stable in a other than ice form?
First of all, the conventional explanation of habitability, to which I think you alluded, is that liquid water is stable on the surface. And so the search for habitable exoplanets usually means that they are Earth mass or something close to Earth mass objects, close enough to, and not too close, to their host star, that they're within the range of stability of liquid water. Although some of us think that habitability as a definition should be expanded to include the possibility of subsurface water, even in situations where the surface is too hot or especially too cold to have water in its liquid form. That is an aside. You asked the specific question, is there even a narrow ribbon of an environment on Mercury where water might be liquid at or near the surface? I think the answer is going to be not at interesting levels of real estate. There's going to be pretty much a dichotomy in the temperature history of areas of the surface between areas that never see the sun and therefore can maintain ices in a deep freeze for millions or billions of years, and objects that sometimes see the sun, in which case they are heated to sufficient temperatures that they cannot keep ice in a stable form. If the ice were thick enough on a planet like Mercury, given the temperature increases with depth in any planet, you could conceivably imagine a Mercury-like body that might have liquid water at the base of a sufficiently thick ice deposit. We don't think the ice deposits on Mercury are sufficiently thick, or the thermal gradient or heat flow coming out of the planet sufficiently high, that is very likely. But since you mentioned exoplanets, there might be larger bodies that have ice deposits in similar frozen states, and if the ice were sufficiently abundant, there might be a liquid water layer. So it pays to keep an open mind when thinking about habitability, but we're all waiting for some of that evidence for a planet that has been altered by its life, as our own planet has, to show up in the astronomical measurements.
Let me move back on this side. Gentleman in that row. Yes. Oops, I'm sorry. We've got two.
One at a time.
Yes, the gentleman forward, and I'll get back to the gentleman in the back.
I may have missed this in your lecture, but is there an association that exists between volcanism and impact craters, or are there separate volcanoes?
Is there a connection between impact craters and volcanism, or is there volcanism that is independent of impact craters?
What you have asked is a question that is very much at the forefront of the messenger science team, because many of the candidates for volcanic centers, the ones around the edge of Caloris that I talked about, the ones that have these irregular depressions surrounded by areas of unusual color that are bright and analogous to lunar volcanic centers, almost all of them are inside impact features. Leading to the question of whether there's a cause and effect that we should explore. Two of the things that an impact crater will do at the time that it is formed might help a volcanic event to occur shortly thereafter. One is that the impact event is energetic, and some of that energy, a small fraction, is deposited as heat below the surface. So if there are conditions favorable to melting and volcanism, an impact event can push a volume closer toward those favoring a volcanic eruption than they would have been before. And the other thing an impact does is break up the near surface and remove any state of stress in the surface rocks that was there beforehand. And because we think so much of Mercury has been under the compressive stress necessary to produce those contractional forms, when an impact crater comes along, it's kind of a stress relief event. And that too could make it easier for magma to come up and form a volcanic feature. So some of us don't think that this is a coincidence, that we're seeing so many volcanic features associated with impact craters. But the jury's still out on all the details. Good question.
Okay, the gentleman in the back who was overstriking the other question. has the rate of volcanic activity changed over the last few billion years?
Almost certainly the rate of volcanic activity has changed in that most of the areas of the surface that we are confident were formed by volcanic processes are quite old. And the big expanses of volcanic plains that were laid down by flood basalts, and even the interlayering of volcanic units that is surmised on the basis of what impact craters can excavate from depth, most of these areas of the crust are older than 3 billion years and approaching 4 billion years. I showed you that one example of a very young impact basin, very young, meaning in the last 20% of the history of the planet, that had interior plains that differed in color and in age from the plains around them, still inside the basin, and that those interior plains showed evidence for once having flowed out over the plains that surrounded them, breaching the mountainous ring that more or less contained it. And so that was an example of relatively young volcanism. But at the moment, we don't have very many examples that are that youthful. And so the thinking is that that the volcanic activity generally waned over time, but we're still on the lookout for examples that fill in the entire history, and possibly for examples that are even younger than the ones that we have documented to date. It is expected that planets, particularly small planets, which have a big ratio of surface area to volume, will lose their heat over time, their interior heat. And that interior heat is required to melt rocks and generate volcanic eruptions. So there is an expectation that the rate of volcanic activity generally decreases with time on a planet, even an Earth mass planet. And for a planet as small as Mercury, 5% of an Earth mass, that should be doubly true. And so far, that is what we're seeing. But we were surprised in the third flyby to find a volcanic feature as young as we did. So we probably don't have the whole story yet.
Okay, unfortunately, this is the last question, gentlemen, all the way here in the back.
Yes, after the 12-month orbital mission is accomplished, what's next for Messenger? What happens to your project?
Okay, after the 12-month orbital period or the nominal mission, what happens next?
I'm delighted to answer that question, considering that Jim Green is in the audience. The answer is that we are funded for 1 year of orbital operations. We are also proposing to NASA that they consider an extended mission for a second year. And we are arguing that we can make measurements in the second year that differ from those in the first year. The sun is continuing to increase in its activity. We're heading toward a solar maximum in 2013. We have enough propellant on board that our Aerojet propulsion system can continue to do the maintenance of our orbit that we need to fine-tune our observations. So we have the expendables, we have the operating spacecraft, the operating payload, we have an agenda that we think is exciting for a second year of observations. If you happen to see Jim Green tonight, you might express your opinion on this matter. But seriously, it does cost money to extend a mission, and NASA must judge the relative merits of any mission extension against all the opportunities that they have for their resources. So we hope that such a thoughtful decision will be made. Thank you. We need you on our senior review.
Please, let's thank Sean again for the great lecture here this evening. I would also like again to thank our sponsors, Aerojet and NASA, and I won't point out Jim Green again. I would like to announce that our public observatory is open now, and there apparently is clear sky. And for those who don't know, that's at the east end of the building. Will someone be there to direct them? Yes, so if you're looking to go out to the observatory.
But Mercury has probably set.
Yes, Mercury may not be visible. Don't forget to turn in your survey if you, or when you leave the theater. Apparently one lucky winner is going to win a door prize. And be sure to join us here again June 9 when we will learn about the Dawn mission just weeks before it arrives at Asteroid Vesta. And any of you who would like to come up and look at the messenger model can do so on their way out. Thank you again for coming.